Um, Welcome everyone. We can now have Mr. Michael Yuan to introduce about how the Western WebAssembly powered microservices. Um, and let's pass the mic to Michael. Thank you.
All right, thank you. So I can start, right? Okay.
Yes, please.
Okay, hi everybody. My name is Michael Yuan, and um, sorry for the delay. I mean, but I'm sure you have just heard Julia, which is another programming language, and so we're going to talk about Rust and WebAssembly here, and I hope you're going to enjoy it. So what we're going to talk about is how Rust and WebAssembly makes Node.js better, makes microservices, web services better. So my name is Michael Yuan, and I'm on Twitter. I'm Juntao, Juntao, and yeah, it's a Chinese name. You can just spell it like that. And my company is called secondstate.io. All right. So if you're interested in Rust, WebAssembly, and microservices, serverless, and things like that, you can sign up our newsletter. And by the way, all the links that I'm going to talk about is all in HackMD notes, so you can see the links to GitHub, the example source code documentation, and YouTube links and all that. And so this is a newsletter. We send out this newsletter about once a week, and it talks about the interesting things that we found about Rust, WebAssembly, and interesting things in this area. Anyway, so first of all, people ask me this question a lot. I'm a web developer. I use Node.js, I use JavaScript. Maybe I used Java in the past. Why should I care about anything else? That's years ago. I think this year is a 25-year anniversary for Java, right? I remember in the early days, back in 2005, that's 15 years ago, I was acknowledged as one of the first Java champions at a big conference called Java One. At the time, Java One conference has maybe 20,000 people in San Francisco, and I was one of the earliest Java champions, being recognized for my contribution for the community, right? But my entry into Java is purely accidental. When I was in graduate school, when I was working on my PhD, we used C++ a lot. We actually do write web applications at the time. That's in the very early days. We write internet applications that you can interact through early web browsers. And when the first time, when people first talked to us about Java on the server side, we were all stunned at how stupid that idea is. Why on earth would anyone want Java on the server side? Because Java was invented for something called applet. It's running inside the web browser. The whole idea is to run a little game. You can that's in the early days. You can even run it on the mobile phone, on your Nokia mobile phone, right? It's to do it on the client side, because that's where you need the bytecode. You need a cross-platform compatibility. Why would anyone want to write Java on the server side? Then there comes the servlet, Tomcat, and then it goes on and on and on. And then before we know it, everybody's using Java on the server side. I'll tell you why in a minute. So that's the first revolution, Java from the client side to the server side. And then a couple of years later, that's after I have done most of my server side work, and I went on to do other things. I went on to do research and do mobile applications. Then a couple of years ago, there's this idea of JavaScript on the server side. It's met with the same incredulity. People like me find it's incredible. That's how stupid that idea is. It's the silliest idea that I've ever heard, is to run JavaScript on the server side. JavaScript is on the client side, right? JavaScript is supposed to be used inside the web browser. Why would anyone want to use JavaScript on the server? But that gives birth to Node.js. And now, before we know it, today, when we come back to look at the web developer landscape, most people, like 80% of the web application developers, use Node.js now. People love to use JavaScript on the server. But that does not negate the problem JavaScript inherently have. It's very, very slow. And other high-level languages like Java itself isn't much better. When you use them to do web application development, it used to not matter, because people used to tell us, the computers, that's the software is always slow, but the hardware is getting faster and faster. So the Moore's law said for every 18 months, the speed of the hardware doubles. So the software that's runs slow today, but saves your developer time, would catch up tomorrow for the hardware. So that has always been that's the conventional wisdom, right? That's why Java was despite it's really slow, it becomes very prominent on the server side. And then years later, JavaScript, despite it's very slow, it's become very prominent on the server side. But it's no longer true, because if you look at hardware, it's stopped improving. The hardware, I think in the past 10 years, the CPU speed hardly improves. That's a fundamentally different world that we live in as web developers, right? So, now if you look, then I said something wrong just now when I said Node.js was a JavaScript. It runs JavaScript on the server. It's only half true. If you really look at Node.js, it's actually JavaScript is only used as an interface language. You use application in JavaScript, but most of the stuff you do still runs in C++. It's the V8 engine that Google developed that translates translate JavaScript into bytecode or a runtime code that are actually being executed on Node.js, right? So if you use Node.js to do image processing or do to do encryption, decryption, it's not JavaScript that does the work. It's C that does the work, right? So the JavaScript calls the C library to do it. So that leads to the landscape that we have today, is that you in order to write high performance Node.js applications, say in big data or in AI or in something else, right? You either have to wait for the C library to be available for JavaScript, or you have to learn C++ in order to write those modules yourself. That's until now. Until now, you can learn Rust, and it pretty much does the same thing. So I have a little table here. As you can see, it talks about different languages and the memory it consumes and time it consumes. And you can see this from native code to JavaScript isn't even on this list. JavaScript actually performs much worse than Python. So if you look at the memory footprint could be a 500 times difference, and if you look at the execution speed, it's hundreds of times difference. Python is like 100 times, 150 times slower than C++, right? So that's that's the world we live in. That's why web developers need to care, because web developers are adopting technologies that go slower and slower and slower and slower, from C to Perl to C to Java to JavaScript, right? But now we live in a world that the hardware is not getting any faster. So we need to squeeze more performance out of the development frameworks that we have. So that brings the question of, if C and C++ is so difficult, or C and C++ get such a bad name, we were using it 20 years ago, and we abandoned it for Java because Java is easier, right? And then for JavaScript, we are not going back to C++, because that's because those are the technologies that's it's very powerful, but it's difficult to use. So if we look at what's replacing C, right, that's where Rust comes in. This is not, this talk is not going to be a comprehensive introduction to Rust, but I just want to tell you, that's Rust was developed, I think 5 years ago by Mozilla. By the way, WebAssembly is also developed by Mozilla. So that's it was used to write the Firefox browser, and in those years, every time when Stack Overflow does a survey, it's one of the biggest developer survey in the world. They have like 60,000 developers participating every year, and Rust is always every single year. I think it's 5 years in a row now, is voted as the most beloved programming language. And a lot of people use it, but people love it. People who use it love it. And it's also one of the fastest growing. And if you look at the programming language popularity index, Rust is, now breaking the top 20. There's lots of, what I would say legacy languages in the top 20, like Visual Basic, right? And so those languages are going down, but new languages like Rust, Go, maybe even Julia, and other programming language are on the rise. So it's a good language to learn. A primer on Rust, again, this is not supposed to be a comprehensive introduction to Rust, but I just want to point out what's so different from what makes Rust so different, right? So it's a language that's similar to C and C++. It's a low level, very powerful language, and it supports most functional and object-oriented programming styles. A lot of people like functional programming styles. Some people who come from the Java background want to deal with objects, and Rust supports both semantics. Right? But the most interesting aspect of this, it has zero cost memory safety at compile time. What that means, one of the biggest innovation Java brought to the table is garbage collection. So you can write, applications without, the developer doesn't have to think too much about memory use and memory pointers, because at runtime, the garbage collector take care of it. That's why, if we go back to the Java plot, if you look at Java's memory use, it's gigantic. It's 500 times C++. It's because the developer is not managing the heap. The garbage collector is managing the heap. It allows the heap to grow to the point where it fills, and then it cleans up the heap, right? So it does it periodically. So for Rust, it's try to enable developers to write bug-free code to begin with. If you look at C and C++ code, they are highly efficient, but 80% of their bugs or important bugs are related to memory pointers. So Rust provides compiler mechanisms that does not allow you to do a lot of things in C++, but it guarantees memory safety. So that's one of the most interesting thing about Rust. If you learn Rust, you find, why can't I do this? Why can't I do that? But then it makes, after a while, it makes perfect sense, because the compiler doesn't want you to do that because it's dangerous, right? So the compiler does a very good job. It's a new way of thinking how to program system. It still allows you to use memory pointers and things like that. That's a high performance, but it does not allow you to do dangerous things with them. And because of that, it does not need garbage collection. So there's no big runtime penalty for that. And because of that, Rust program runs almost as fast as C and C++ native code. And there's extensive use of generics and closure, those new programming concepts that has emerged in the past couple of years, and it's not available in C++. And it has a package management system, Cargo. It's very similar to NPM, and if you NPM in JavaScript and in Ruby, you have Gem, right? But in C++, there never been a comprehensive package management system out there. So Rust brought in a lot of new concepts that developed in the past 5 years into C and C++ and make it better without a big performance hit. So, one of the things, I really do encourage you guys to learn a bit of Rust. And, one of the things that you would find is something that's very interesting is that the compiler is really like, a lot of people say Rust compiler is like a nanny, or it's like a teacher, right? That's it not only tells you that you are wrong, it tells you why you are wrong, and often tells you how to fix it. So I've not read the screen here, but you can see the error messages the compiler gives are phenomenal. So you don't have to read a huge book to learn Rust. You can just start writing programs, and then the compiler would fail, and the compiler would tell you how to improve it, how to change it, right? So those are interesting things about Rust. So because Rust, like Go and C++ and all the other languages, unlike Java, it can compile into a native binary. So basically, compile into a binary that you can directly execute on your Linux system, on your Windows system, right? And because of that, you can write web applications that way. Like if you write a web application in Go, it's you compile into a binary, and then you run the binary application. The binary application listens to a port and serves HTTP or HTTPS, right? So so the web server, instead of like JavaScript or Java, there's no external application server that manages the application, but instead the application itself is embedded into a binary, and then you use that binary to serve HTTP, right? So that's when people say they write Rust-based web application, that's what they mean, right? So there's frameworks that allow you to do that. For instance, rocket.rs, that's a website. You just search it on Google and you'll find it. And, that allows you, give you a framework that where you can write, URL routers, to say when a GET request comes in and here's how I'm going to respond, things like that. So that's one way, is to compile a native binary application. And the second way to use Rust code on the web is to, like I just said, Node.js is actually running on native code. Node.js only provides a JavaScript interface, but it provides an extension mechanism that is fully native, right? So you can actually compile Rust application into a library that extends existing runtime like Node.js. So that's Node.js has an API framework where you can have .so libraries that directly plug into that. So then from JavaScript, you would be able to call those library functions. So that's the second way to use it. Compile to native, but not to a not to a standalone application, but to a library, and then put that library as an extension to Node.js, right? So the second way to do it. The third way to do that is actually the most interesting, and that's what we would like to talk about, right? It's to compile into a bytecode and run inside a managed container, much like Java or JavaScript does, right? Now people ask, why? You just said, those managed applications are slow. So now that's why you need to use native application to have Rust compile into native application and then run those native applications because they're fast, right? But now why would you now take the native application and run it in the managed container? As it turned out, there's many reasons. That's the oldest reasons is why, I think almost 20 years ago, why web application moved to Java from C++. It's because Java is managed code. We don't really want to run native code on the server. We want to run managed code. Because the first thing is security, is that it's especially important for untrusted code. There's a lot of code that's you write yourself that you think it's trusted, yes. But a lot of times you need to run other people's code. Either you provide a service that allow other people to upload code, or you are just running open source components that other people have published on the web. Oftentimes you have no idea what's in it. You just don't know that it's gonna accomplish some tasks that you ask it to do, right? That's so to run it directly on the operating system like native code is dangerous, because there could be things that it does that you are not fully aware of, right? So for security reasons, it's really important, especially if you have a large library ecosystem, to be able to run untrusted code. And the second is the code that need access to hardware. You really need to have a security model that does not, allow all the application access to hardware, or not allow any application access to hardware, right? So for security reasons, running managed code is that reason alone is sufficient, I think, for most enterprise use cases, that we need that level of security in order to, and that level of security you cannot get by running native applications on unprotected operating system, right? And of course, runtime safety is that when the application crashes, it should not crash the operating system. It could not cause memory overflows, buffer overflows that allow people to access other parts of our operating system, right? So runtime safety is another really important issue. And then that's the same issue Java solved all these years ago, is a platform independence. That's when I have an application that is in managed code or bytecode, I can run it anywhere I want. I can stream it. I can put it in the database, and I can put it in the cloud, whatever. I don't have to think, is this the right version of Linux? Does it has the right library? Does it has the right CPU? It's ARM versus Intel, in order for me to run this. And, because once you start to do that, then the management overhead becomes very, you have a lot of management overhead. You have to be able to version it. You have to be able to, have ways to determine, the host environment and match that with the binary. So cross-platform independence is a management issue, and it's very important. And then, of course, manageability, because managed code runs inside some kind of containers, right? So it's you can do package management and storage. You can do automated deployment. You can do hot swapping and things like that without shutting down the application. you can do none of this with a native application. So that's why, even with language like Rust, which can produce high performance native application, for web developers, you still want to run it as a managed code, as in the managed container instead of what we call naked native code, right? That's so you don't want to run it on unprotected operating system. So now we said Rust is a high performance language that can compile to native code, but then I said something to contradict it, to say that but we don't want to run native code, we want to run managed code. So that's where a container comes in, right? Because you can run native code inside a container. And the thing, the container most of us familiar with is Docker. I have a I have a native application, but I don't want to run it on my own computer. So, in case it crashes or whatever, right? So I start a Docker instance and run inside Docker, and a lot of people do that. But Docker has its own set of problems. It takes a very long time to code start because it starts the entire operating system, right? It drags in the entire OS and the runtime stack. So if you want to run JavaScript in Docker, just imagine, the kind of software stacks that you have to install in order to run this, say a hello world, something like that, right? So it's caused even slower startup time, and it's caused the runtime to have a very large size, even for very simple tasks, and it's very large memory footprint. So all in all, for web application tasks, that's you send in a request and expect a response back. If everything has to run inside Docker, you're gonna take forever. It's very inefficient way to run things. Unfortunately, that's how a lot of cloud providers are doing today. If you look at the Amazon Lambda function as a service, it's almost entirely built on Docker. Although it doesn't have, it does a lot of optimization. For instance, keep your runtime up and running. It doesn't cold start every time a new request comes in. So you try to make a lot of management compromises. But still, Docker takes a lot of memory, and it's in general pretty slow for tasks like this. So last year, March 2019, that's seems eons ago. That's before the COVID virus and all that. So Solomon Hykes, that's if you look at his bio, he's a co-founder of Docker. He invented Docker. And he sent out a tweet like this. He said, WASM plus WASI, WASM is WebAssembly, had existed in 2008, we would not have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. It's to say, we recognize there are lots of issues with Docker, but for running server-side code, maybe there's a better container or better virtual machine that can have all the benefits of the managed code, like I just said, the safety, security, cross-platform, cross-portability, manageability, and all that, but without the heavy overhead of Docker. And what he identified is WebAssembly, right? So what is WebAssembly? Well, as you might have guessed, it's what we call lightweight managed runtime. So it's in a sense, it's almost like Docker, but it's a lot lighter, and so it starts a lot faster. And strikingly, similar to the history of Java and JavaScript, it's also originated inside web browsers. If you just remember what I said, right? Java originated in web browsers as applet. JavaScript originated in web browser as a scripting language, and WebAssembly also originated in web browsers. And it's actually now widely supported by all browsers. It's supported by 90% of all browsers out there. The chances are on your phone or on your computer, there's a very good chance your browser already supports WebAssembly. It's supported by Google, Microsoft, Apple, Mozilla, it's basically, all the major tech companies. It's provide excellent binding for JavaScript because it was invented because it was invented as a browser technology. And what's the most popular language in browser? Of course, JavaScript, right? So WebAssembly provides excellent binding for JavaScript. And that really helps on the server side with Node.js, right? So you can now see the connections here. And it's a great compiler target for Rust programs because it supports the LLVM compiler toolchain. It's in Rust and in Cargo, the Rust package management system there has been deliberately a lot of support for WebAssembly targets for the Rust programming language. So of course, it also has binding for Rust, right? So so that's put those two and two together. It's originated in web browsers and provide excellent for JavaScript support for JavaScript. It's also provide excellent support for Rust. Now we have a runtime that is lightweight, efficient. It's about 1,000 times faster than Docker at startup time and 50 times faster than Docker at runtime. That is a perfect server-side container that run managed code. That's you could write in Rust, right? You're writing Rust, compiling WebAssembly, and then run it on the server inside of WebAssembly. So that's the history I talked about, So it's actually not that surprising if you know the history of those technologies. 20 years, about every 10 years this happens. 20 years ago, Java made the move. 10 years ago, JavaScript made the move. And now we think Rust and WebAssembly making the move, right? In a nutshell, the architecture that we are describing has three important components. The first is that we leverage the ease of use of JavaScript. There's a famous law from Jeff Atwood. Jeff Atwood is the founder of Stack Overflow. It's a website we all use, right? He said anything that can be done in JavaScript will be done in JavaScript, right? That's why, because it's so easy to use. Everybody loves to use it. Or, I wouldn't say everybody loves it. Everybody loves Rust, but, people think, it's really easy to prototype in JavaScript. It has a very large ecosystem, so it's so we need a solution that needs to support JavaScript and the whole ecosystem behind it, right? And then we have Rust that has a high performance, high developer productivity, and the memory safety, very low bug rate to write high performance modules in the web application. Then we have WebAssembly that allows us to tie those two together, to provide a safe environment for Rust applications, and then to connect to the JavaScript ecosystem. So it looks like this. So at the top is the Node.js JavaScript runtime, and Node.js JavaScript runtime has two, some of the tasks, some of the JavaScript goes to the C++ based runtime engine, and some of it goes to the WebAssembly based virtual machine. The WebAssembly virtual machine has access to the operating system, has access to databases, has access to AI hardware through a permission system. And it runs applications that compiles from Rust, right? So essentially, you are writing a Node.js application in JavaScript, but this JavaScript is going to be able to call functions that are written in Rust. So you have computational intensive tasks or heavyweight tasks that are written in Rust, compiled to WebAssembly, and then you can call them through JavaScript. So that's the architecture of this whole thing. So now let's look at some examples. I'm sorry, I'm presenting this, so I'm not looking at any of the questions that you guys may have. We can interact later, once we are well done. Okay. So the hello world example is actually really simple. The top, the first block of text is the Rust function. So the Rust function, you can see it's very simple. It's the function name is called say. It takes a string variable and returns a string. It basically, put hello in front of the string that you pass in, right? So if you pass in world, you're gonna say hello world. You're gonna return hello world, right? So that's a very simple Rust application. That's and you can see the syntax of Rust. I think it's fairly easy to understand, right? Just join two strings. The second block of text is the JavaScript. What the JavaScript does is import the package that allows JavaScript application to call the Rust application, right? So the Rust application runs inside WebAssembly. There needs to be some code that glues those together. And so that's the first line to say require this compiler generates this starter.js file for you, so you don't have to write it yourself. So those two lines of code is literally are the two lines of code that you need to write yourself. And so inside JavaScript, you can call a function as if it's a JavaScript function, and pass in a parameter to say Rust, right? That's a JavaScript function. but it's translated into the Rust function and then passed to the Rust function and then gets the result back. So we can see the results in the third block. So we run this application, we node app.js. It first runs this, it goes to call the JavaScript function. JavaScript function calls into Rust function. Rust function says print. Rust function say received X or received Rust into the console. It does that into the console, and then it returns to the JavaScript. And JavaScript console logs the output of this Rust function, the string value that returned from Rust, right? So it returns hello Rust, right? So that's all very straightforward. That's demonstrated the whole process of creating a function in Rust, and then in the JavaScript host environment in Node.js, how to call that function from JavaScript. I hope this is very straightforward. I mean, this is literally 10 lines of code, and now you have a fully working Rust hello world that's running inside the Node.js environment. But let's see another example that's maybe more complicated. So that's example, maybe we can see the bottom panel first. The bottom panel is how we run a web application in Node.js, and now we point the web browser to it. It solves this equation that ax squared plus bx plus c equals to 0, right? So you can put in a, b, c, and when you say solve, it does the AJAX call into the Node.js endpoint. The Node.js endpoint makes a call to the Rust function that actually solves this equation for you, and then it prints out the results, right? So that's the whole thing, and that requires 20 lines of code, maybe 25 lines of code. So at the top left, you can see that's the Rust function. The Rust function is just to solve, and the solve, it comes in. It takes the 3 parameters because the way that we structured it is to say we want this to be done as a web service. So the input parameter is actually a JSON array. The JSON array has the 3 floating numbers, right? That's we unwrap them and get those 3 numbers, and then perform those math. That's to figure out what's the roots of that, of the root solution of this function, right? And then return this. If we can find the real root, we return the root as a JSON array here, like we have demonstrated those 2 floating numbers and floating point numbers. That's as a JSON array, right? If there's no real root, the root are not real numbers, then we return a. Actually, it's not right. It said it's. The return value should say not real, not rational, because you could have perfectly irrational numbers but real, right? So we should return a not real number to the calling function so that we display that the roots are not real in the web interface, right? So this is the Rust function that perform. This is a self-contained Rust function that perform this computation. It takes the 3 numbers wrapped in the JSON, and then returns a JSON that has those 2 roots wrapped in it. So then we look at the Node.js application that actually calls this Rust function. So the HTML calls this Node.js application, and Node.js application calls the Rust function, right? So this, when you hit the solve button, it calls the /solve endpoints, and that takes those 3 function parameters and then just call the method. It just puts them into a JavaScript array and pass that into the JavaScript function called solve. This solve function gets translated into a Rust function called with the same name, and then the parameter passed into the Rust function, and then the results come back and it sends back to the web browser, right? So this is another example. That's but you can imagine. There's much more complicated computation that you can do rather than just finding a solution for formula like this, right? So all those links are available, in the HackMD notes, and you can. There's a lot of documentation to help you with different kind of tasks that you can do with Rust and that you can do with Node.js, right? It takes a couple minutes for you to start it, and I promise it's very easy. And but if you want something even simpler, you can use the template. The template you can just fork it, right? That's then you will be able to run it on your own machine, or you can open it in Visual Studio code spaces. You can have an online IDE that has nothing to do with your computer, and then you can start to edit those Rust code and run the server from there. And it's not only it runs on Node.js, it runs on Dino too. So if you have, you guys know about Dino, right? That's Node.js spelled backwards, and that's the founder of Node.js started this project. It's a TypeScript runtime. It's also based on V8, but it's underneath. It's not C++, but Rust. So, but for our purposes, we can also compile Rust applications into WebAssembly and run it inside Dino. So, there's some detailed explanations in this repository as well. So go check it out. So this is how, this, the template repository I just showed you, this is how it works. You go to the GitHub repository, and then, you click on that, create code space button. And once you said that, once you have this code space button, this whole UI opens up in the browser. And then now you can edit the code and run it and, access it from the server. It's now repeats again, so that's all, the Microsoft thing. Microsoft, if you have a Microsoft Azure account, it gives you enough credit for you to try this entirely for free for a month or two. That's not a problem. So that's so it allows you to edit the Rust code, edit the JavaScript code, and run the server, and then test the server to see to make it say hello and all that. So that's if you go to the GitHub repository I have just shared, you will be able to see this demo, and you will be able to repeat the whole process. It's fairly easy. So now some shameless promotion, why SSVM? That's what we talked about. You all know that I work for a company called Second State. So the Second State virtual machine is called SSVM, right? So we talked about the benefits of WebAssembly. But there's a bunch of WebAssembly runtimes out there, including Google's V8. There's Lucet, there's a bunch of them. The thing that we find that's, that we excel is that we do very well in terms of benchmark, that we are one of the fastest ones. Of course, we compare with Docker plus native, meaning that compile native application running inside Docker container instead of running inside those WebAssembly. You can see the Docker native almost, is slower than almost every cases, right? But WebAssembly is faster, and we are SSVM is among the fastest WebAssembly engines out there. Anyway, so sorry. I'll leave you to watch that video yourself, because that's because it's difficult for me to get the audio work. But that video shows to write a function in Rust that does TensorFlow, that does image recognition, and it allows you to run inside the Node.js application, allows people to submit an image, and then use the TensorFlow model in Rust to do the high performance computing to find out what's on that image and return the results. And we have demos that has this image recognition model running on the not only on the CPU but also on custom hardware, right? That's the AI inference chips, and through WebAssembly, and allows the whole result to be completed. If you use AI inference chip to do image recognition, that's about 1,000 times faster than CPU again, right? So we are looking at the code start time, WebAssembly versus Docker. It's already 1,000 times faster, and if you have custom hardware, it's another 1,000 times faster. So we are looking at, for some use cases, it's 1,000,000 times faster, right? So it's the benefit is huge, and I personally do think Rust is going to be an indispensable tool for web developers in the future, and it's not to write to use Rust framework to write WebAssembly to write web applications, but instead to compile Rust functions into WebAssembly and then use it in a function as a service environment or in a Node.js environment. So anyway, thank you very much. I think that's all I have, and I probably exceeded my allocated time. So thank you.